Okay, we're going to start chapter 8 today, taking a look at confidence intervals. And this is really our first look at what's considered an inference procedure for trying to estimate a parameter about a population. So we're just going to kind of talk about the basics here in this first section. And then in the next section, we're going to exclusively look at creating confidence intervals for estimating a population proportion. And then section 8.3 will be creating confidence intervals for population means. So what our goal here with confidence intervals is it's to try to estimate the value of a parameter based on a statistic that we've collected. Remember, statistics come from samples, parameters represent populations. Okay. We're also going to be calculating probabilities that would describe what would happen if we were to use the inference method many times. Okay. So if you just look back at the chapter that we just finished, it says in chapter 7, we assumed that we knew the population parameter. However, in a lot of real life situations, it truly is impossible to really know what that population parameter is. So the situation that we were setting up in chapter 7 wasn't really a very realistic scenario. For example, if we wanted to know how long does a new laptop battery last, we're not really going to be testing all the laptop batteries and let them all run dry so that they go completely dead, and then we have our population parameter. Like, we wouldn't be doing a census for that. Or if we want to know how much does the weight of a quarter-pound hamburger at a fast food restaurant varies after cooking, we're not going to weigh all the uncooked burgers in the United States. Okay? And so more realistically, in statistics, we are needing to look at what's called a point estimator. And what a point estimator is it is simply a statistic that provides an estimate for a population parameter. So these could be things like a potential mean, a potential standard deviation, a potential proportion, interquartile range, median. Honestly, the two that typically are focused on in AP Stats are trying to estimate a population mean or trying to estimate a population proportion. Okay, so the value of that statistic from just your sample that you took is called a point estimate. It's just a single value, and it is really just what we would say is our best guess at what we think the unknown parameter is. Okay, it's not super accurate, but it is just what our best guess would be. So let's look at an example here. It says in each setting, we are asked to determine what the point estimator is, and then we would calculate the value of what the point estimate is. Okay, the point estimator is the statistic that we are using, and the point estimate is the value of that statistic. So here it says you want to estimate the mean time that all Dover High School AP Bio students spend studying biology. A sample of 10 students was taken from AP Biology students, and they were asked how much time do they spend studying AP Bio each night. Below are the results. So here we have in hours here the amount of time that each of these 10 AP Bio students said that they spend studying bio. Okay, there were two questions here. They wanted us to determine what is the point estimator that we are using. And so if we're looking for, how much time are they spending, we would be finding the sample mean from this sample. So X bar is the point estimator. Okay, X bar is the point estimator. And then if we were to actually add these up and divide by 10, the actual value for X bar is 2.15. 2.15, I'm going to label that hours, is what we would call the point estimate. Okay, point estimate is the value. The estimator is what the statistic is. Okay, because here they were asking us to find the mean time. All right, now you can see in example B, it says what proportion P of U.S. high school students smoke. The 2011 Youth Risk Behavioral Survey questioned a random sample of 15,425 students in grades 9 through 12. Of these, 2,792 said they had smoked cigarettes at least one day in the past month. Okay, so you can see here that we're focusing now on proportions, not means. So we're going to be using this information to find a p-hat, which is a sample proportion. So p-hat is what we're using as our point estimator. And now to actually calculate the value of p hat, looks like they sampled a total of the 15,425 students. It said of those, 2,792 said that they had smoked at least one day in the last month. So that roughly comes out with a value of 0.18. So 0.18 is what we would call the point estimate. Okay, the point estimate there. All right, let's go ahead and move on here to the next page and see how this is all going to kind of link to what we would call a confidence interval here. Again, in the last section regarding sampling distributions, we always had the true population parameter. They gave that to us in the problems. But in reality, that's just never going to happen. I mean, if you know that value from your population, then why are we even trying to gather a sample? It feels like we must have had access to the entire population in order to get that parameter. So in reality, what we really typically have, statisticians that is we just have data from one sample, and that creates one point estimate or one sample statistic. Okay, so let's look at this example here. It says, how smart are we really? So for the end of your year stat project, you want to estimate the average IQ of the senior class at Dover High School. In order to do this, you're going to take a simple random sample of just 16 seniors. You're going to have them take an IQ test on an iPad app. After collecting the data, this is what you discover. The average IQ for those 16 seniors is 115. Okay, question 1 says, is 115 a parameter or a statistic? Label and measure with the proper symbol. Well, obviously, the 115 came from just a sample, so that would be a statistic. The proper way for us to label that would be X bar. So then it says, what is your best guess for the value of the true mean IQ of every senior at Dover High School this year? Okay, and this goes on to say, this is what your point estimate is. By the way, when it says the true mean, that is referring to the population mean. Okay, so our best guess is really just whatever we got for our sample mean from those 16 seniors. It's 115. Okay, now the question goes on to say, how confident are you that your point estimate is exactly right, and why might it be incorrect? Well, we could probably say that we're not confident that it is exactly right. And our reasoning could be because every sample essentially yields a different sample mean. Okay, we learned that when we did sampling distributions. Okay, so every sample is going to yield a slightly different sample mean. Okay, so here's what we're going to focus on here. It is true that while our point estimate is actually just our best guess for what the true population mean IQ would be for Dover High School students, it doesn't actually give us any indication of how close the estimate is to the true population value. Okay, it's just kind of this single value. If we were to estimate the population mean, and we'll say that it's 115, our estimate could be off by 3 IQ points. That's not that much. Or it could technically be off by 30 IQ points, which really feels like that's a significant variation there. So it does kind of feel like there's this practical need to kind of know how close is our point estimate likely to be from the true parameter. And so this is where confidence intervals enter onto the scene. What confidence intervals do is they give us a range of values for which that true parameter is likely to fall within. So for example, if I were to make the statement, instead of saying our best guess is the average IQ of Dover High School students is 115, but rather saying something like the population mean IQ of Dover High School seniors is probably somewhere between 110 and 120 IQ points. That feels like giving a range like that is a little bit better. Okay, so let's take a look here at how to construct confidence intervals and kind of this idea behind them, because confidence intervals generally distinguish what percent we want to be confident that we are actually going to be capturing the true population mean within the interval that we're creating, okay? So let's say that we wanted to be 95% confident that we're going to capture that true population mean IQ of Dover High School students, okay? So we would then find the standard deviation of our sampling distribution for X bar. And the reason that we are going to multiply that by 2 is because if you think back to the empirical rule, remember the empirical rule says if the shape of your distribution is normal, okay, if you stretch out one standard deviation on each side of the mean, that holds 68% of the data. Remember, if you stretch out 2 standard deviations from the mean, that should hold 95% of the data. Okay. Now, please note that this is only going to be an accurate method if the sampling distribution is approximately normal. So I'm assuming a few things here just to be able to have this little discussion here with this example. We'll definitely break down the details of this here with other examples. But let's just suppose that I got from my sample, okay, I took a new sample of 16 seniors, and my X bar revealed that the average of those 16 seniors for their IQ was 109.2. Okay. Now, if we were to assume, and I realize that this is a big assumption here, but let's just assume for the moment that the standard deviation of the population of Dover High School seniors is 10. Okay. Now, what I would want to do, and if you recall, the standard deviation for the sampling distribution for sample means is this formula right here, and that's on the formula sheet. Okay, my sample size was 16, so that's why I put a 16 underneath there. And then you can see we were just given in this problem, just for the discussion of this example here, that the population standard deviation of Dover High School seniors here would be 10 for their IQ. Okay, so I'm coming up with the population, the standard deviation for X bar, my sampling distribution, is going to come out to be 2.5. Okay, so what I'm going to do is I'm going to take my point estimate, that's this 109.2, and I'm going to create this range, create this window by adding and subtracting 2 of my standard deviations, not of the population, but of my sampling distribution, which we said was 2.5 here. Okay. If I were to type that in on the calculator, going through once with addition and again with subtraction, I would get an interval from 104.2 to 114.2. And you'll notice there's a comma right here, but that comma is almost read like if I told you tonight I want you to do problems 1 through 9 on the homework, and we always put a dash there. That's how the comma, like interval notation, is basically acting here. Okay, so this would be our 95% confidence interval. It's 95% confident because I multiplied my standard deviation for my sampling distribution here by 2 because stretching out 2 standard deviations should capture 95% of the data. Okay, so let's break down what these things are here. Okay, just first, confidence interval. Confidence intervals are always denoted by a specific percentage. I will say 95% is the most commonly used confidence intervals, but you're going to be asked to calculate 90%, 98, 99% confidence intervals. What a confidence interval, is it gives you an interval of what are called plausible values. And that word plausible simply means believable. Okay? You're creating a range of believable values for your parameter. Okay, and the interval is calculated essentially using this kind of generic formula right here. Okay, you're going to take your point estimate, and so for us, that's either going to be our sample mean, X bar, or that'll be our sample proportion, P hat. And you're going to add and subtract a margin of error. Now, look back at the example that I just did here. My margin of error was found by multiplying my standard deviation of my sampling distribution by, and I got this 2 based on the fact that I wanted to be 95% confident here. Okay, something worth noting is that your margin of error, as your margin of error increases, okay, so as my margin of error goes up, look at how that's going to affect the confidence interval, okay? Think about this here. The confidence interval is going to go which direction? If you take your point estimate and you add and subtract your margin of error, you're going to get a larger confidence interval if your margin of error is larger. So if as your margin of error increases, the confidence interval will also increase. Now, we're going to focus on this a little bit more here later, but the confidence level is specifically talking about the percent. For example, if you were to construct, say, 100 different 95% confidence intervals, okay, and they'll all be slightly different from each other, but what the confidence level is we're saying, well, we would think that 95% of all of the possible confidence intervals that we constructed, 95% of them should be capturing where that true population parameter is located. Okay. Now, something that will need to absolutely be memorized is how to interpret a confidence interval. Okay, and it's basically this small little template right here where we would just kind of fill the blanks in. We would say we are blank % confident that the interval from, and then you would fill in the 2 values from the beginning and end of your interval, captures the, and then you would state what the parameter is in context that we are trying to estimate here. Okay, let's practice this with example 3 here. It says you take a random sample of U.S. adults, asking them if they're interested in exercising more. Based on this poll, a 95% confidence interval for, look at what we're estimating, the population proportion who are wanting to exercise more is, and then here's our interval. Okay, so for right now, we're not going to focus yet on how to actually create the interval, but just how to interpret the interval. So you can see the template up above here. It's asking us to interpret this confidence interval. So we're going to say we are 95% confident that the interval, and then we're going to state what that interval is, from 0.45 to 0.57, captures the, and now here's where I'm putting the context, and you can see I highlighted it right here. It captures the true population proportion of U.S. adults, okay, that's what who we're talking about, U.S. adults wanting to exercise more. Okay, absolutely crucial that we just don't say we're 95% confident that the interval from 0.45 to 0.57 captures the parameter. Okay, we always need to use context. Now here's part B. It says, what is the point estimate that was used to create the interval? Well, in other words, they're asking, so your point estimate should be in the exact middle of where your interval is. Look at the formula back here again. Remember, we take the point estimate, we add and then subtract the margin of error, and that creates the interval. So your point estimate should be exactly in the middle. So this is just a matter of taking the ends of your interval, adding them together and dividing by 2, and that then would tell you where the center is. And make sure you're labeling that with the correct symbol. We are talking about proportions in this example, so that should be labeled p hat. Okay, now the question is, well, then what is the margin of error? Well, now that I know that the center of the interval is 0.51, I can take either one of the 2 ends, it doesn't matter which one, and I just need to find the distance from one end to the center, and that gives me the margin of error, ME, to be 0.06. Okay, part D says, a newspaper prints a claim that based on this poll's results, more than half of U.S. adults, now more than half, if we're talking about a proportion, means more than 50%. Okay, so the claim in this article is that more than half of U.S. adults are interested in exercising Okay? We want to use the confidence interval to evaluate this claim. Now look at the interval. The interval, while it does have some proportions that are greater than 50%, there are also some that are less than 50%. And so here's what we're going to say. We're going to say since 0.5 and values less than 0.5 are included in the interval as plausible values, there is not convincing evidence that more than half of U.S. adults are interested in exercising more. Okay? We want to be really very convinced. And so if it feels like there is a chance that it could be less than 50%, or for that matter, even 50%, that is our evidence that, look, we don't have enough convincing evidence. Now, hypothetically, if our confidence interval was 0.51 to 0.59, we would have arrived at a completely different conclusion. We would have said, since all the values in the interval are above 0.5, there is convincing evidence that more than half of U.S. adults are interested in exercising more. Okay. So we're going to wrap this video up with just this last page here. I want to talk about a common mistake with interpreting confidence intervals. It is absolutely incorrect to be using the term probability when you are trying to interpret a confidence interval. Okay. Here's a mistake people say. The probability that the population mean is in the confidence interval is 95%. Now, the reason that's wrong is because a population parameter is fixed. We know that when we take samples, we get a different statistic every time we do a sample, but your parameter is the truth. That's like if you did a census. Your parameter is fixed. It's not changing from one sample to another. The parameter is what it is. Okay, so since it's fixed, it can't be in an interval 95% of the time and then not in the interval 5% of the time. Okay, so we never use the word probability when we're interpreting. We always just want to kind of stick to this interpretation here on the previous page. All right, let's look at example 4 here. It says you take a random sample of how many texts teen girls send each day and another random sample of how many texts teen boys send each day. Now, this is really important here. It says then you calculate the difference in the means. Based on this poll, the 95% confidence interval for the difference, girls minus boys in their texts, in their population means is, and then here is our confidence interval. They're asking us to first just interpret this interval. And so we're always going to start out with the percent that we are confident. This was a 95% confidence interval. So we're going to say we are 95% confident that the interval, and then we just simply state the interval here, the interval from negative 2.5 to 7.9 captures the, now make sure we're looking at what this interval was based on. It was based on the true difference, okay, the difference in population mean texts sent per day. And we should probably distinguish what the order of that subtraction is. And so I'm going to use really good communication here and just in parentheses say the difference was girls minus boys. Okay, now the question is, what is the point estimate that was used to create this interval? Remember, the point estimate should be located directly in the center. So I'm just going to take the endpoints. I'm going to add those together. I'm going to divide by 2. The point estimate, now remember, this is the difference in the mean number of texts that girls sent and the mean number of texts that boys sent. So I'm going to label that x bar sub g minus x bar sub b. Okay, the question next is, what is the margin of error? So you can take one of the endpoints of your interval, subtract the center, the point estimate from it, and that difference would give you the margin of error, 5.2. Okay, now here's the question. Does the confidence interval give convincing evidence that there is a difference in the population mean number of texts sent by teen girls versus teen boys? Justify your answer. Now remember, we did girls minus boys. Let's pretend for a moment that there's no difference at all in the average number of texts sent by girls and boys. If there was no difference, then when we subtracted those, we would expect to get 0. Okay, there's no difference. If they're the same, subtracting two numbers that are the same is 0. Okay, so what you're looking for when it asks whether we have the evidence of whether there is a difference, you want to look and see, was 0 a plausible value in your confidence interval? Okay, so I'm going to say this. If there is no difference, then the difference is 0. So, as long as 0 is a plausible value in the confidence interval, then we have convincing evidence that there is no difference in mean texts. Again, girls minus boys. Okay. Now, I understand that there were other numbers in the confidence interval other than 0, but anytime it asks you whether there's evidence showing that there could be a difference, okay, then if 0 is even a possibility, if 0 is plausible, then that is evidence that there is no difference. Okay. So they're asking us in Part E to make up an interval in which you would conclude that the interval reveals that there is not convincing evidence that there is a difference in the population mean number of texts sent by teen girls versus teen boys. And as long as you create any interval that doesn't include a 0 in it, you're fine. Okay, so I'm just going to create an interval from 2 to 8. You'll notice 0 is not a plausible value, so that means that I would conclude then for this that this would be convincing evidence that there has to be a difference because 0 wasn't even a plausible value. Okay, let's talk quickly about how to interpret a confidence level, and we'll focus more on this in the next section as well, and we're going to wrap up with just some miscommunication here and improper interpretations for some of this. Okay, to say that we are 95% confident basically means that if we were to take many, many samples, and it has to be of the same size from our population, we would expect 95% of them to be capturing the actual parameter. Okay, now I want you to notice that these are considered improper interpretations, and when you go to do problem 19 on your homework, these examples here should really help with this. Okay, the first thing says the interval that you create provides plausible or believable values for either a mean or a proportion. It is not creating plausible values for your individual measurements. So it is absolutely wrong to say we are 95%, or we're confident that 95% of all dogs have a heart rate between 150 and 188. You're supposed to say that we would be 95% confident that all dogs have a mean heart rate between 150 and 188. These intervals are supposed to be either about means or about proportions, not individual measurements. The second mistake here, we should not be using the results of one sample to predict the results of future samples. So it is absolutely wrong to say we are 95% confident that future samples of dogs will have a heart rate between 150 and 188. Okay, we should not be making future predictions here. Okay, the population mean does not change. Okay, it doesn't change. A parameter is fixed. So it's just what it is. So it is absolutely incorrect to say that if we were to take many samples, the population mean heart rate for dogs would be between 150 and 188 in about 95% of those samples. Okay, that's suggesting that 95% of the time, the population mean is between 150 and 188, and then 5% of the time it's not. Okay, what's changing is our confidence interval. Every time we gather a new sample, it creates a slightly different interval. The interval can change, and so because the interval is changing, it could possibly capture where the population mean is located or not, but it's not the population mean that's changing. Okay, and finally, we're only 95% confident that the population mean heart rate is between 150 and 188. So it is wrong to say that the mean heart rate of dogs cannot be 192. Okay, remember, these are only confidence intervals. Okay, so it's not leaving out of the question that the actual population parameter could be located outside of that interval that you've created. Okay, the last example here says we're discussing whether the interval is capturing the mean, not whether the mean is in the interval. So make sure you get that in the right order. And if you just follow those templates, it really helps. The mean is constant for a problem, doesn't change. So the interval can change based on your sampling distribution's mean. Okay. Please make sure that you are avoiding using the term probability in any of your interpretations. Okay, there's a few problems there for you to go ahead and try that go along with this video.